a case study of water. So, the properties, the thermodynamic properties. So, these are thermodynamic properties of water we are interested to compare. Thermodynamic property, then result from experiment and result from molecular dynamics after generating so many conformations and then taking the ensemble average over them, ensemble or time average. So, the thermodynamic property, the first one is the potential energy of water in kilojoules per mole. Let me see the values. So, the experimental value, so this is in kilojoules per mole. So, the experimentally measured value of U is minus 41.5. From MD, the measured value is minus 41.4. So, you just can see how reliable or how accurate the simulation can be. The next property is the density, gram per cc. The experimentally measured is 0. The accurate value 0.995, and from MD we get 0.998. Diffusivity, the diffusion coefficient in centimeter square per second of water. Experimental value is 2.4 into 10 to the power 5 to the minus 5, and what you obtain from here is 2.5 into 10 to the power minus 5. So, as you can see, we can reproduce the experimental data very well by choosing the right force field parameters. So, this shows the robustness of MD simulation technique to generate the microstates, and after we generate the microstates, we take the ensemble average or the time average to get the properties for which experimental data are available. So, the advantage of the computer simulation technique is that we not only calculating the thermodynamic properties and matching them with the experimental data, we can also we can always go back to our microstates and pick up each and every microstate and see what transitions had happened. When you take the ensemble average, we just get a single ensemble average or time average value. That does not give the microstructural information or the transitions happened into the system that we are tackling. But those information are available in my computer simulation data. I can always go back to my time evolution information, and from here I can get that this is the structure of my protein ligand complex where the binding was the most, or binding was the strongest, versus the one where the binding was the least. So, what computer simulation techniques are giving is that they are first getting the confidence that my technique and the models are good enough, and therefore I can reproduce experimental data, plus it is giving more insights, INSIGHTS, it is providing more insights about the system, about my system's microstructural information. So, I think that is it from statistical thermodynamics part of this course. So, I'll just want to summarize, and if I summarize, I would say that we started with the definition of statistical thermodynamics. We said that thermodynamics and statistical thermodynamics, they basically can be applied to the same system, where thermodynamics, the classical thermodynamics, gives relations between various quantities, thermodynamic quantities. Statistical thermodynamics tells us the magnitude of these thermodynamic quantities in terms of the very constituent of the system. So, statistical thermodynamics assumes that a system is composed of the tiniest particles of atoms, and it looks at how these atoms interact with each other, and based on those atomic level information, it predicts the extent or the magnitude of the thermodynamic properties. So, where thermodynamic properties give the relation among the thermodynamic quantities, statistical thermodynamics tells why the thermodynamic quantities are more in one system versus they are less in another system. So, statistical thermodynamics basically gives the microscopic information of a system, whereas thermodynamics gives the information of the macroscopic quantity. So, in the first few lectures, I talked about microstates and macrostates. I defined the microstates and macrostate in a quantum system to start with, a small system, and there first we have looked at the Boltzmann distribution law, which is a very important distribution law in statistical thermodynamics, and we have seen that if we can find out a microscopic quantity called partition function, that partition function is related to can be related to any thermodynamic quantity. So, we written down some of these relations, how partition function is linked to thermodynamic quantities like entropy, enthalpy, Gibbs free energy, Helmholtz free energy, and we have shown that once we get the partition function Q, then all these thermodynamic quantities can be easily obtained. But in that context, we have seen that the initial formalism had some problem, and those problems, one problem in the formalism was the entropy. The entropy was not coming right, and Gibbs found that out for the first time, and he named it as Gibbs paradox, and later Gibbs paradox was resolved by reformulating the formalism, and that was the Boltzmann era. So, until the Boltzmann era, people could use the partition functions and get the thermodynamic quantities for small systems, and in that context we also have looked at the partition function for a monatomic gas. But then when we come to a bulk liquid system, or our system of interest, our systems of interest were biological molecules, and for biological molecules, using partition function in terms of the quantum states were very difficult to use, because quantum states just for the ground state could be in the order of 10 to the power n, where n is number of particles. And therefore, for a classical system like our biological system, large systems, we had to take a parallel parallel formalism, where we basically got the partition function not in terms of the quantum states. We got the partition function in terms of the different distribution of our system. So, when we basically got different distributions of our system just by defining their R and P, by defining their positions and momentum, we generated we often different microstates. So, once we generate different microstates in a classical system, and that was ensemble approach by Maxwell Boltzmann, particularly by Gibbs. So, Gibbs introduced ensemble approach, and in that ensemble approach, we can generate, if we can generate different microstates of a system, and then we can take their average and we get the ensemble average or the time average, and that's the thermodynamic quantity what are measurable experimentally. So, we defined the ensemble average of a thermodynamic quantity. We define what ensembles are, we define what ensemble average is, we define what time average is, and then we basically wanted to see how we can generate different microstates. So, by definition, if we have different microstates, we can just take the average over all these microstates and get the ensemble average. But then how to get all these microstates? So, in that context, we introduce molecular dynamics simulation, which is a computer simulation technique, and there, by solving Newton's second law, we generated different microstates of our system of interest. We found that we could generate as many microstates as you want, depending on what kind of computer resources we have. If you have a very powerful computer resource, we can generate millions and billions of microstates, and if we take average over all these microstates, we get the time average, and that time average matches very well with the experimental data. We took an example of liquid water, the bulk water, and we found that for liquid water, the MD calculated values match very well with the experimental data. Apart from molecular dynamics simulation, we also briefly talked about Monte Carlo simulation technique. Monte Carlo simulation is another computer simulation technique where we can generate new conformations of a system using random number generator. While in molecular dynamics, we solved Newton's second law, we basically solved differential equations to generate new conformations. In Monte Carlo, we use random number generators, to obtain new conformations. Molecular dynamics and Monte Carlo both are having advantages and disadvantages. Molecular dynamics simulation advantage is that it has the time information, so you can always go back and pick up the particular conformation and find out how that conformation is linked with all other conformations. Whereas in Monte Carlo, and therefore molecular dynamics simulation will be much more expensive in terms of computer resources. Whereas Monte Carlo simulation, it does not keep the history in the memory. It just looks at the preceding configuration and generate the new configurations. So since it does not have the time information, and Monte Carlo simulation is faster than molecular dynamics. So these two techniques helped us to generate several microstructures, several microstates, and once we have the microstates, we can calculate the average property of any thermodynamic quantity, and that's the whole information I wanted to give you from statistical thermodynamics aspect of biomolecules. Thank you for listening.